So I was wondering, was there in the development of the models for these case studies any guidance from theory on what to include and what not? Or was it really based on strong knowledge of the individual cases?
So really the only formal simulation modelling was in the third example in Chillico Lagoon. And that was essentially informed by a causal loop diagram that was created through consultation with stakeholders and the literature in terms of the key components within the model, and then creating as much, compiling as much information and data in order to parameterize that.
There's always the researcher who has to come up with his own ideas about what are relevant feedbacks and such, and in an interaction with the stakeholders locally. But I was just wondering how we make these models. If there's something that tells us, hey, this is how we should develop. Hey, if you introduce this, you make the model worse. If you do this, you make the model better. It seems really that it is a deep understanding of a specific case that you build these models in this way.
I don't know how to generalize. I'm not sure that we've kind of taken one concrete line or the other. I mean, at the moment with the second example in Erhai, we have a student who's trying to create an ABM model of the eutrophication process, and the plan is that she'll link that to a kind of systems model for the catchment. So there will be a kind of hybrid model that looks at social and the environmental feedbacks between the two. But the ABM model is there really to try and capture the emergent nature of the eutrophication process and see whether or not we can actually test what we've hypothesized as the loops that are coupling together in order to trigger that collapse. I don't know whether that answers your question, but that's
halfway. My worry is a little bit that if a different group would have gone there, they would have made a different model, come up with completely different recommendations for treatment. So how can we constrain this huge model space?
Yeah, well, I'm not the mathematician in our group, and nor the modeler. I mean, maybe people here would have a view on that.
Does anyone want to comment? I think the issue of competing models is such an intriguing one, and so you've done your best to incorporate your understanding and that of the stakeholders into your model, and I'm very impressed by how it performs and stuff. But so in general, it seems to me we do need to have other people come up with competing models if there are other understandings of the processes that underlie what we're modelling, and it's easy to compare the performance of the models, and we have statistical methods that will do all that stuff.
I would agree with that.
So, I mean, following on from that, there are techniques, of course, to detect possible tipping points in time series data. So even before we construct models, are there those techniques sufficiently reliable that we can say, are there tipping points given what we see in the time series, even before we've constructed a detailed model? Question, really.
Yeah, and we use those breakpoint analyses in all of these examples. Actually, I mean, I haven't shown them. There's a lot of other stuff.
Yes, I think in terms of sort of early warning signal analysis, I think that's come along quite a bit in the last few years, as far as I can tell. It's not my particular specialism, but.
So I've been taught the theory of bifurcations, tipping points in the past, and now I'm doing more database modelling. I've always struggled to join the two up, and I kind of want. I mean, one thing I wonder is if you've spotted in your data that you've got a hysteresis or something, are you doing it that way around, spotting it, and then deciding on a model which is going to lead to a hysteresis, or do you make your model do some runs and see if you're seeing a hysteresis in the results. Which way round do you tend to come at the problem?
Well, personally, I guess. For example, the example that I was talking about with the AMOC, that came out of a discussion with modelers in Met Office who had seen this hysteresis in their time series. I guess there's a big debate on exactly what evidence there is for AMOC reversals from the paleo record, but then they came up with a model that they'd already developed, and it was quite clear that that was enough to explain the hysteresis present in their data. Yeah.
And in in our second example in Erhai, where there appears to be what looks like a fold bifurcation in the data, that's why we're using ABM. We're trying to see whether we can capture that in the modelling process, and that's primarily because the key thing in Erhai is that they don't know what to do in terms of management to restore the lake. They don't know how much emphasis to place on environmental regulation of runoff from new dairy farms in the catchment. They don't know what to do with sewage treatment. They don't know what to do with the exotic fish which exist in the lake, and nor do they know what the optimum water level is, because it's been manipulated in the past because of hydroelectric power. So you've got this multi-dimensional set of questions, and we're just hoping that we can get some sense out of an ABM coupled with a systems dynamic model of the catchment to help them do that, with no presumptions on whether that's a fold bifurcation or not. But we'd hope to see it actually in the model outputs.
This is a naive question, I'm afraid. How are you handling uncertainty, or trying to handle uncertainty in the different parameters to determine whether or not you get a tipping point, what kind of tipping point you get, whether you skate over the surface or bounce into the new state? Are there routine methods for trying to kind of look at uncertainty in that space?
Well, I can only talk about the Chillico Lagoon example where Greg has used a Monte Carlo sensitivity analysis to basically set a whole array of trajectories just to try and tease out what are clearly defined safe trajectories that never collapse, and those which have much higher probability of collapsing, of going below a maximum sustainable yield.
Hi, Robert McLaughlin. My first one, can't really formulate a question, but I'm from New Zealand, and everything you said about the lakes in China, you could say it would be identically true in New Zealand. Half the lakes have flipped over to a eutrophic state. And
that's a shame.
Been extensive modelling and research, but still no regulation. So I guess I was very struck by your final point, where communicating the conclusions effectively and simply is perhaps a very important part of it. Is that the take-home message from your study?
Absolutely. Yeah. Couldn't agree with you more.
No easy
Thank you.
answer there. Then my second one is a question. When you see this S-shaped curve, for example, in the data indicating hysteresis, mathematically that suggests that there would be a second parameter and there would be a cusp bifurcation, and that this S-shape would transition smoothly into something without an S-shape, which suggests you should be hunting for a second. What is that second parameter? Is that
I can't say. I couldn't say. There are certainly two other key drivers in the process, and that is water level and carnivorous fish, which eat all the zooplankton, which would have ate all the phytoplankton.
I mean, maybe just as a general point, in that one of the feedback strengths should be enough to take you back to a cusp, but I can't tell you which one.
I'll try to shout from the back. It's just to both of you, and thank you very much for the interesting talks. I was just thinking, we can try to identify tipping points once they occurred. Is there anything to do? Can we actually do something to predict when they happen? I mean, there's been some work a long time ago done on critical slowing down and oscillations that could warn us that we're actually approaching the tipping point. And I was just going to ask what your opinion about the possibility of predicting it before it occurs and maybe doing something about it.
Yes, I mean, certainly the sort of promise of early warning signals for tipping points is very compelling, and well, it would be fantastic if we could have reliable ones. There has been a lot of progress, as far as I'm aware, in trying to quantify their reliability in the last 5 years or so. I'm happy to give one or two references that I'm aware where this is being done, but it's not something I'm working on particularly. I don't know if anyone else in the audience can give an update on that.
Well, there's a large literature from statistical mechanics of phase transitions, amongst which signals of large fluctuations in the system as a precursor of phase transitions is one of the standard signals that one sees near tipping points.
It would be interesting to see whether it can be applied in real systems.
Sorry?
It would be interesting to see whether it can be applied in real systems, like big ecological systems. That
Exactly.
My view is that I think people who work with real-time series data in ecosystems and probably several other kinds of environmental systems, I think the jury, they'd say, was out, because I don't think it's been as conclusive a method for detecting up-and-coming tipping points as perhaps the theory would suggest. What we've recently started to do is to move away from those indicators in the frequency domain and actually start to think about the structural, the architectural changes within the system that theory also predicts should happen as the system becomes more and more unstable, as it loses resilience. So we've started looking at we've started to be informed by network science, which would suggest that the arrangement of associations between components within the system should have predictable changes as they lose resilience. So we've been looking at, for instance, the nodal degree of associations in species within a particular trophic level, and looking at the skewness of that distribution of nodal degree as a metric as to how stressed the system is, and that's looking quite promising, actually.
So, well, just to reiterate what was initially said there, it might be an interesting line of inquiry to see if complex models that include stakeholders and agents and so on could be investigated using methods similar to statistical mechanics to understand if these have tipping points that can be mapped back into the real world. So personally, I don't think that you can go and study the real world immediately. You still need to have something of an intermediate simplification of complexity, and then perhaps jump onto the real world. But I think it might be an interesting one.
Yeah, so very interesting that point, John, about whether you can map onto a network and see how the linkages are changing to look at stability. I think that's the sort of thing we ought to be thinking about quite a lot. But the whole issue of detecting tipping points, we normally think about it as something we want to avoid, a tipping point, and it might be that when we're thinking about policy change, we actually want a kind of tipping point, a different way of doing things. So it might strangely be easier to ask the question, how hard do you have to push the system at any one point to change its state? So, let's get to a more sustainable world or different land use. How would we reforest how hard you have to push, which is a bit like saying how much incentive or whatever.
Yeah.
That might be, strangely, a more practical question, because it relates to this whole issue of how the resilience of the system is changing. And it might, strangely, just at the moment, be more policy relevant to actually say, what would you have to do to change the landscape in this way?
Yeah.
And that, in some ways, that's a better question, I think, to try and address than the normal one, which is, can you detect in this natural system variability that change? Like, well, what would I have to do to change it? Turn it on its head.
Really like this idea about safe decisions. I used to work in the aircraft applications and safe technologies, and they would be safe over a time period, and you try and understand what the degradation of that period would be, and draw a line. I wonder whether the kind of decisions we make about environment and landscape also have an implicit time period that we're talking about, and whether that's something that needs to be more explicit.
Yeah.
Safe for how long? Safe for who?
Yeah. Well, I'm sure you're right. Yeah, so I think that's context specific. I think it depends on, the rate of climate change in your area, the rate of population growth in your area, what you think is going to be the economic forecast for your area, I think experimentation is the key there, and also it comes down to stakeholders. What's their their policy horizons? I mean, if you're in a system where you are limited by just politicians working to 5-year horizons, it may be rather different to someone who has the opportunity for a long-term strategic plan.
Problem, isn't it? Safe over the political cycle is really
in Chillico Lagoon, we were guided by the fisheries managers who said, well, we would really like something over the next few decades. That they felt they had that opportunity to lay down some regulations that they could have a chance of enforcing. But they wanted to look at options that didn't have answers that involved saying move a lot of people out from the area. They wanted to keep them in the area. They wanted to look at alternative livelihoods, but they still wanted a large fishing population to be remain. So these are kind of social choices which then informed the structure of the model, or at least the structure of the scenario and future forecasting.
I just wanted to mention that there is one is when we are working on modeling, and all the work we have been doing, we're thinking on DEFRA or policymakers as a clients of whatever we do. And I wanted to just bring here, the insurance institution, because, for example, we are working on a project where basically what the insurance are trying to build is a product that they can sell to Caribbean countries, Caribbean islands, to protect the coastal protection of the coral reef ecosystem. So if a tipping point is a hurricane happen and collapse the coral reefs, how fast, which management do we need, and how costly is that management to recover the coral reef and the coastal protection? So it's basically the work that you have been doing in terms of, which kind of management, compensation or banding fisheries or not, to avoid a tipping point, but it's looking at instead of from the recovery perspective. What kind of, I have already happened, something stochastic happened, and hurricane happened, recovering, and do I need to compensate the fishermen not to fish, or do I need to do something on land, but to faster that recovery? So the insurance institution, I think, is very interested on this analysis, and I just thought that to mention it.
Yeah. Okay. Thanks for your comment.
Do you mind if I just go back to Peter's question right at the beginning? Yesterday we were talking about spatial scales of different things interfering with each other you talked about temporal scales of different things interfering with each other. In terms of translating through space and exchanging that for translation through time, could you just amplify a little bit more about, I mean, does the idea of bifurcations as you move through space work, or is it much more complicated because you've got two parameters, or am I being very, very naive about this?
Well, I guess, there are approaches to looking at, say, pattern formation in space where you use bifurcation theory, or even use a spatial variable instead of a time variable. I'm not quite sure what I can say beyond that, but I'd be very happy to have a chat after this, maybe. Sounds like it's a more detailed question.
I was going to say, gosh, it was a good dinner last night. Not sure whether the coffee's out there yet, but
We'll find some.
we'll find some. Anyway, can we thank the speakers again for